Hi guys, Dr. J here, and in this video we're going to be walking through an example Monte Carlo simulation method, and I've got the example pulled up for us here. So we are using a toy problem, a reservoir storage model, where we are assuming that reservoir storage or aquifer storage is simply area times thickness times porosity. So a volume times a porosity is going to give us a storage. This is a simplified model, but for our case it's useful for illustrating how Monte Carlo simulation works. And we have three parameters: porosity, layer thickness, and layer extent. The extent we're going to assume is a known constant, and so we have porosity and layer thickness, which we're going to simulate or draw realizations from in order to calculate uncertainty in the total storage volume. Now, we aren't told how we found this out, but we're going to assume that porosity is Gaussian distributed with a mean of 27 plus or minus 3%, where the 3% there is the standard deviation. And we're going to assume a uniform distribution for layer thickness between 10 and 14 meters. With this information, we can jump over into Google Sheets and simulate this problem using a bunch of the information that we've already learned about, such as transforming distributions and probability density functions. So the first thing that we're going to want to do, if I just come back here for a minute, is simulate a distribution, a Gaussian distribution with a mean of 27% and a standard deviation of 3%, and a second distribution of layer thickness, which is going to be uniformly distributed between 10 and 14 meters. Now, the way to do this is to keep in mind what we've learned about transforming distributions, and we can start out by using the built-in functionality in Google Sheets to generate standard uniform continuous distribution realization. So I can use a function called randarray in Google Sheets, and I'm going to give it, let's say, 1001 as the inputs to that function. If I do that, I'm going to end up with a sheet which has 1,000 numbers in it, 1,000 numbers uniformly distributed between 0 and 1, so it's a standard uniform distribution. We can just verify that that's the case by pulling up a histogram. I'm going to go to Insert Chart, come over here to the chart type, and then change that chart type to histogram. And now we can see we are more or less uniformly distributed between 0 and 1. The variations from uniform are just due to the sample size. If we had 10,000 samples or 100,000 samples, we would get something which is exactly uniform. So I verify that I have a standard uniform distribution here in this first column. And now what I can simply do is transform this distribution into a new distribution, which is the ones that I need. And I need two distributions, so I'm actually going to do this twice. I'm going to have the first column be my first set of random numbers, and then I'm going to do the same thing in a second column, and I'll give myself a space here. So now I've got two distributions, and just to verify that these are at least uncorrelated, let's just take a quick look at a scatter plot. Here's a scatter plot. And basically, we don't see any correlations here. We don't see any evidence of anything other than independence. So we're going to assume that these are independent variables, and we can use those to build up our two distributions that we need. Now, for the uniform distribution that we need a uniform distribution between 10 and 14 meters. That's for our layer thickness. And that's very easy to get from our standard uniform distribution. We can simply translate and scale the standard uniform distribution. So what I'm going to do is I'm going to take our standard uniform variable, multiply it by 4, and add 10. So the 10 gives us the correct lower bound, because the lower bound on our standard uniform is 0. And the 4, multiplying the variable by 4, gives us the correct upper bound. So whereas our maximum before was 1, now our maximum will be 4 times 1 plus 10, so that's 14. And I can go ahead and autofill the rest of that column. So now this distribution should be uniformly distributed between 10 and 14. And again, just quickly looking at the histogram chart, we can verify that that is in fact the case. So we have a uniform distribution between 10 and 14, which we've gotten by simply stretching and translating the original uniform, standard uniform distribution. Okay, so now we've got our uniform layer thickness variable worked out. Now we're going to take our second set of standard uniform numbers and transform those to a Gaussian distribution with a mean of 27%. To do this, we're going to use conceptually the same exact techniques that we've used before when we've transformed distributions. We're going to assume that each one of these numbers here, these are all numbers distributed between 0 and 1, these are all going to be considered probabilities. So for a probability of 0.3588667, we're going to determine the x value from a Gaussian distribution with a mean of 27% and a standard deviation of 3%, which has the probability of 0.3588 on the cumulative distribution function. Now, if you didn't quite follow that, go back and check out the videos I posted on transforming distributions. What we're going to do here is use a built-in function for doing that same thing that we did graphically before, which Google Sheets has built in, which is the inverse normal distribution function. It's going to take a x value, which is our probability here, a mean and standard deviation. So first value is just going to be our standard uniform variable. Then we'll have a mean of 27% and a standard deviation of 3%. And we'll go ahead and autofill. And now we have here a distribution which is exactly a normal distribution with a mean of around 27%. One thing to keep in mind is that this is percent, so we'll need to take this and divide by 100 when we're actually doing the calculation for volume. So what have we done? We've taken two standard uniform distributed variables, random variables, two different random variables that are independent. We've transformed one to be a new uniform distribution between 10 and 14 meters. And we've transformed the second to be a Gaussian distribution using the inverse CDF functionality available in Google Sheets to be a Gaussian distribution with a mean of 27% and a standard deviation of 3%. And now what we know is that our area, our extent of our reservoir is 40,000. And I'm going to go ahead and just fill in this number, in the same number in all these different columns. And now I can very easily just simply calculate what the total volume or the total storage volume is for each one of these realizations. So I'm going to be multiplying layer thickness times porosity divided by 100 times areal extent of the reservoir. And now what have we done? We've obtained 1,000 random realizations, random in the sense that they are drawn from the distribution, which is represented here by multiplying layer thickness times porosity times area extent. So now what we see is that we've got some values here for the total storage volume. And this is going to be in cubic meters, so we'll need to keep track of our units. This is total storage volume in cubic meters. Our layer thickness was in meters, and our areal extent was in square meters. So now we just have cubic meters, and we have what looks to be a Gaussian distribution, or similar to a Gaussian distribution, but it's been a little bit stretched by that uniform random variable of layer thickness. And so it's a little bit wider than a true Gaussian distribution would be. And so now we could, if we were more interested in barrels, we could do the conversion to put this in barrels. For now, I'll just leave this in cubic meters. This is a very useful technique because it doesn't really matter what our function is or our formula that we're putting it through. In this particular case, we had a relatively simple formula of layer thickness times porosity times area. But you could imagine doing all sorts of other types of simulations with more or less complicated functions. And if we know something about the distributions of the input variables, and we know what things are constant, then we can simply use this kind of a technique to simulate what our final distribution would be. And this is actually a very common technique to do, where you don't necessarily know how to convolve these distributions mathematically. In this case, with a uniform and a Gaussian, we could actually do the math and work out what the final distribution would be. But it's much simpler to draw realizations from each one of those distributions and then put those through our formula and calculate what the final distribution would look like. And by increasing the number of simulations from 1,000 to 10,000 or 100,000, we'll get a very good sense of what this distribution would be. And then the good part is that we now have an empirical histogram or an empirical distribution representing our final outcomes, the outcomes that we're interested in. The total storage volume in this very simple toy problem, but perhaps you're interested in production from a reservoir or total storage capacity in a new CO2 sequestration reservoir. Whatever it may be, you're able to use this distribution now to make decisions. So perhaps you have a go, no-go decision. In this case, maybe you need to know what the storage volume is, and you need a minimum volume of, let's say, 1 million cubic meters. And in this case, you'd be able to say, well, what the probability is of having a volume less than 1 million and a probability of having greater than 1 million. And you can do that by simply counting the number of realizations which are greater than or less than 1 million cubic meters. So this wraps up this particular example. Just to jump back here to the example page, this can be done in a very similar way that we did in Google Sheets, except using functions in NumPy. So give that a try. Let me know how it goes, and I'll see you next time.